Today, we're diving right into a totally fascinating breakthrough straight out of Brown University and the University of Michigan. It's a discovery that is literally rewriting the rules of material science and quantum technology. Okay, let's dive into this. Have you ever wondered how solid metals actually change their shape? Well, when metals heat up and physically transform, the way their individual atoms reorganize is this incredible, invisible mystery. It's a puzzle that has completely baffled scientists for decades.
Part 1. The Metal Morphing Mystery.
Imagine the atomic structure of a metal. We generally have two main arrangements. First is face-centered cubic, or FCC, which is super tightly packed with particles at the corners and faces. Then you have body-centered cubic, or BCC, which is less dense with just a single particle at the center. Now, the fascinating part here isn't just the geometry, it's the behavior. Metals can suddenly switch between these two arrangements when they heat up. Take iron, for example. At exactly 912 degrees Celsius, it violently shifts from BCC to FCC. But what exactly happens right in the middle of that shift? For years, scientists have never been able to clearly see that exact in-between stage. Historically, it's just been a complete ghost.
Part 2. Catching the Missing Link.
So, for the longest time, researchers relied on something called the Nishiyama-Wassermann pathway. But it was just a leading theoretical model. It basically predicted that during these dramatic metal transitions, there should be a series of really short-lived, highly unstable intermediate structures. You can think of this pathway as the legendary missing link. Material scientists have been absolutely desperate to capture it so they could fully understand and actually control nanomaterial engineering.
The big problem, of course, is that these intermediate phases are naturally way too unstable to just sit there and be observed. As a metal transforms, it rushes through this awkward middle stage so unbelievably fast that you simply cannot catch it in action. Since researchers realized they couldn't just watch it happen in nature, they had to get creative. They decided to engineer these intermediate phases from scratch, literally recreating and stabilizing the impossible from the bottom up.
Part 3. Playing with nanoscale Legos. And this is where we meet our heroes, nanoscale architects Oh-Chen, Tim Moore, and Yasutaka Nagaoka, who completely changed the game.
Now, what's really interesting about this slide is how they actually pulled it off. The team developed a precise three-step process, which they recently published in the journal Science. First, they synthesized entirely custom silver particles that they called mecons. Second, they coated these particles with molecular hairs. And third, they carefully assembled them into perfectly ordered structures known as superlattices.
Let's talk about these custom mecons. They are made of silver nanoparticles, but what makes them special is their shape. They possess a highly specific, truncated octahedra shape. Basically, think of a 14-sided geometry that kind of looks like a diamond with its corners sliced off. This shape is absolutely crucial because it acts as a perfect hybrid between a sphere and a cube. The research team meticulously adjusted their heating conditions to produce mecons with the exact right degree of roundness. That specific shape allows them to pack together in ways that normal, everyday spheres or cubes simply cannot.
Oh-Chen from Brown University summarizes their whole approach perfectly. He said, "Our work is a little bit like kids playing with Lego blocks. We synthesize unique, nanoscale building blocks and stack them into interesting structures." I mean, how cool is that? These brilliant researchers are quite literally custom designing microscopic silver nanoparticles and stacking them like childhood toys to solve one of the biggest mysteries in material science.
And remember those molecular hairs from Step 2? Tim Moore from the University of Michigan explains it beautifully. He noted, you can kind of picture them like hairy particles. The hairs are flexible enough that the particles have more freedom to shift, but they also fit together nicely. These long molecular chains act just like sticky connectors. They gave the mecons just enough freedom to move around, allowing them to mesh together and miraculously stabilize those elusive Nishiyama-Wassermann structures. They actually did it. They built the missing link.
Part 4. Room temperature quantum tech. So the crucial point is, we are now pivoting from a purely structural puzzle to a massive, totally accidental technological payoff.
When the researchers exposed these newly assembled silver superlattices to light, they observed a truly mind-bending behavior. It's called deep strong light-matter coupling. The electrons inside the silver nanoparticles began to oscillate in perfect synchrony with the light waves. They became completely quantum mechanically entangled. It's literally light and matter dancing together so perfectly that they are essentially functioning as one singular quantum system. Now, normally, traditional quantum materials require extreme sub-zero freezing temperatures just to work. We are talking about needing massive, expensive cooling infrastructure just to maintain that entanglement. But this new silver superlattice,
It exhibits those exact same highly sought-after quantum entanglement behaviors without any of that extreme deep freeze cooling.
And this brilliantly illustrates the holy grail of this entire breakthrough. They achieve these incredible quantum optical effects at standard room temperature. No liquid helium required, no absolute zero environments, just the regular ambient temperature of a room you or I might be sitting in.
What you really should take away from all of this is how profoundly this completely changes our entire technology landscape. By stabilizing this one missing link, they have created a concrete, real-world foundation for accessible quantum computing. It entirely opens the door for next-generation sensing technologies and highly advanced quantum systems that can operate in everyday environments rather than just being locked away in highly specialized, ultra-cold laboratories.
As Ochen pointed out, anytime you are able to identify a brand new phase of matter, completely new applications are inevitably going to emerge. So I will leave you with this question to ponder. Now that we actually have the ability to stabilize the unstable and unlock quantum entanglement at room temperature, what impossible technologies will we build next?